Well, this is CS50, and already this is week 4. And recall that last week, week 3, we began to explore the inside of a computer's memory a bit more. We talked about arrays, which were just chunks of memory back to back to back that really laid things out left to right, top to bottom. And this is actually a pretty common paradigm. Even if you're new to programming and certainly new to C, you've kind of seen this approach of just using memory in some way to lay things out, like images, for instance. So for instance, here is a photo taken of last week's front row, for instance. And this is kind of an opportunity to explore exactly what happens if we start to zoom in and zoom in and zoom in, because it seems like most any TV show, like CSI, whatever, or any movie that explores forensic information might have the investigators sort of zoom in on an image like this to see what the glint in someone's eye is, because that reveals like the license plate number of someone that just drove past, right? Something that's a little over the top there. But there's an opportunity here to speak to why that is so unrealistic. For instance, let's zoom on this puppet here's eye, and let's zoom in a little more to see what might be reflected. Let's zoom in a little more. And that's it. There's only finite amount of information if you have an image represented in this way using pixels, these dots on the screen as rows and columns, because if you're only using a finite amount of memory, then at the end of the day, you can only store a finite amount of information. And at least I don't really see in this grid here any glint of a license plate or something like that that you might otherwise see in Hollywood. So today we'll explore sort of these kinds of representations of how you might use memory in new and interesting ways to represent now very familiar things, but also start to explore what some of the limitations are of this representation. But consider, after all, that this doesn't need to be even as high resolution, as many pixels as something like this other image. You could imagine just doing something silly with Post-it notes like this. And if you think of an image as just having rows and columns, these rows otherwise known as scan lines, something we'll explore in the coming week, you could make this sort of fun smiley face by just using 2 different values, maybe a 0 and a 1, or yellow and purple, or vice versa, just to kind of make something come to life. Now in practice, recall, we talked about storing not just a 0 or 1, but maybe an R, a G, and a B value, like 24 bits or 3 bytes in total. But we'll come back to that. That would just be a more involved image. But if for fun, if today you sort of want to tackle something passively in the background, if you go to this URL here, we've put together an opportunity to do a sort of a bit of pixel art. If you go to this URL here, that'll redirect you to a Google spreadsheet if you have a laptop with you today. That'll look a little something like this, which we've sort of organized in rows and columns. So if you'd like to go ahead and use Google Spreadsheet's colorization feature to color in those individual squares, if you'd like, see if you can't make something a little creative, and then email it to Carter, and we'll exhibit some of the best or favorites on the website thereafter. So let's transition then to something a little more familiar, images. And not all of you have used, presumably, Photoshop, but you're probably generally familiar with Photoshop as a program for editing and creating images or photos or the like. And here is a screenshot of Photoshop's color picker, via which you can change like what color you're going to draw with the paintbrush, or what color you're going to fill in with the paint bucket. It's representative of any kind of graphical tool. And there's kind of a lot of information in here, but there's perhaps some familiar terms now, R, G, and B. In fact, right now, this is Photoshop's way of saying you're about to fill in your background or foreground with the color black. And that appears to be represented with an R, a G, and a B value of 0, 0, 0. Or alternatively, using a hash symbol and then 0, 0, 0, 0, 0, 0. And if some of you have already made web pages before and you know a little bit of HTML and CSS, you probably are familiar with this kind of syntax, like a hash symbol and then 6 or sometimes 3 digits thereafter. And if we look at a few different colors here, for instance, here might be the representation of white. Now the R, the G, and the B values went way up from 0 to 255, 255, 255. Or alternatively, it looks like Photoshop, and in turn web browsers, could represent that same color white with FFFFFF. And let's just do a few others. Here is red. And it turns out that red is a whole lot of red, 255, but no green, no blue. Or AKA FF0000. So there's perhaps a pattern here emerging. Here is green, 0, 255, 0. AKA 00, FF00. Or lastly here, blue, which is no red, no green, but apparently a lot of blue, 255 again, AKA 0000, FF. Now, some of you, again, might have seen this notation before, these zeros and these Fs and all of the numbers and letters in between. But this is another form of notation. And in fact, we'll explore this today. Really is just a precondition for talking about some other concepts. But the ideas ultimately are really no different. What we're about to see is a different base system, not just binary, not just decimal, but something we're about to call hexadecimal. But first, recall that with RGB, we previously did the following. Any RGB value, red, green, blue, just combine some amount of red or green or blue. So here we have 72, 73, 33, which in the context of an email or a text, of course, said what a couple weeks back? Just hi with an exclamation point. But in the context of a Photoshop-like program, this might instead be representing collectively this shade of yellow, for instance, when you combine that much red, that much green, that much blue. So here's the same idea. If you've got a lot of red, no green, no blue, together that's going to give us red. If you've got no red, a lot of green, no blue, that's going to give us, of course, green. If you've got no red, no green, a lot of blue, that, of course, is going to give us blue. So there's a pattern emerging here where apparently 0, 0 is none, as always, and FF is apparently a lot. And it's maybe somehow equated with 255, at least per that Photoshop screenshot. Meanwhile, if we combine one last one, a lot of red, a lot of green, a lot of blue, that's actually going to give us a single white pixel like this. All right, so think back. Here was binary. In the world of binary, you had just 2 digits, 0 and 1. Could have been anything else, A or B, X or Y, but the world standardized on these numerals, 0 and 1. In our world's decimal system, of course, you have 0 through 9. As of today, though, we're going to start using hexadecimal sometimes in the context of images and also files, just because it's a convention. And there's some conveniences to it, where now you're going to be able to count up to F in a notation called hexadecimal. From 0 through 9, then you keep going to A to B to C to D to E to F. The idea being each of these, even though it's weirdly a letter of the English alphabet, it's still just a single symbol. It's not 1, 0 for 10 or 1, 1 for 11. All 16 of these values, these digits, so to speak, are indeed still just single symbols. And that's a characteristic of just using this other notational system. So how do we get from 0, 0 and FF to something like 0 and 255 respectively? Well, this hexadecimal system, aka base 16, just does the math from week 0 and really grade school a little bit differently. For instance, if you have a number that's got 2 digits, or hexadecimal digits as of today, the columns are just a little different. Instead of powers of 2 or powers of 10, which we saw for binary and decimal respectively, it's powers of 16. So if we just kind of do the math out, that's the 1's column, this is the 16's column, and so forth. Things get actually pretty big pretty quickly in this system. But now let's just consider how we would represent familiar numbers. If you've got 2 hexadecimal digits, for which these hashes are just placeholders, 0, 0 is going to mathematically equal the decimal number you and I know, of course, as 0. Why? Same thing as week 0. 16 times 0 plus 1 times 0 is the number you and I know as 0. And we can count up from here. This, in hexadecimal, would be how a computer represents the number we know as 1. It would be 0, 1 in this case. This would be 2, 3, 4, 5, 6, 7, 8, 9. In decimal, we're about to go to 10. But in hexadecimal, to be clear, what comes next? So apparently A, so 0A, 0B, which is now 10 or 11 or 12, 13, 14, 15. So using hexadecimal is just kind of an interesting way of using single symbols now, 0 through F, to count from 0 through 15. And we'll see why it's 15 in a moment. But as soon as we get to F, anyone want to conjecture how in hexadecimal, aka hex, do we now count up one position higher? What comes after 0F in hexadecimal? So 1, 0. It's the same kind of thing. Like once you're at the highest digit possible, F, or in our decimal world, it would have been 9. You sort of add one more, and 9 wraps around to 0. Or in this case, F wraps around to 0. You carry the 1, and voila, now we're representing the number you and I know as 16. And we could keep going forever, literally. This could be 17, 18, 19, 20 in decimal. But let's just wave our hands at it and count as high as we can, dot, dot, dot. The highest we could count in hexadecimal with 2 digits just logically would be what in hexadecimal? Something, something. FF, I heard. So yes, that's the biggest digit possible. So FF is what we have. So how high can you count in hexadecimal if you've got just 2 of these digits? Well, it's the same math as always. 16 times F, aka 15. So that's 16 times 15 plus 1 times F, or 1 times 15. That gives us 240 plus 15 in decimal, the result of which, of course, now is 255. So this hexadecimal system you may have seen in the world of web pages, and if you haven't, we'll get to that in this class in a few weeks, or we just saw in the context of Photoshop, just has this sort of shorthand notation of counting as high as 255, but just calling it FF. Now, it's marginal, but that's like 50% savings of how many digits you need in order to count as high as 255, because in decimal, of course, 255 is 3 digits. In hexadecimal, you can count as high using just 2. And that difference is going to get magnified the bigger our numbers get. Let me stipulate for now, you're going to get more and more savings in terms of just how many symbols you need on the screen to represent bigger and bigger numbers than that. All right, let me pause here just to see if there's any questions thus far on what we've called hexadecimal, which again just gives us 0 through 9 as well as A through F. Any questions or confusion? And if it feels like we're lingering a bit much on arithmetic, we're not really going to see other notations besides this moving forward. These are sort of the go-to 3 in a programmer's world, typically. But there are some others. Yeah? Good question. Does hexadecimal require more storage or less storage than a decimal system? Theoretically, no, because this is just a way of representing information. And we'll see in a concrete example in a moment. But inside of the computer, at the end of the day, you're still storing bits. And using hexadecimal is not using more or fewer bits. Think of this as how you might write it down on a piece of paper, just how many digits you're going to write, or on a computer screen, how many digits you're going to see at once. But it doesn't change how the computer is representing information, because all they're representing at the end of the day is zeros and ones. So in fact, let's go there. If this, a moment ago, FF, I claim was 255. Let's just rewind to week 0. And if we wanted to count to 255 in binary, that's as high as you can count, recall, with 8 bits. And there's only a few of these numbers that are useful to memorize. Like 255 is as high as you can count with 8 bits if you start at 0, because 2 to the 8th is 256. But if you start at 0, it's 0 through 255. So in binary, recall, if you have 8 bits, all of which were ones, and I won't do out the math pedantically here, but if I do this plus this plus this dot, 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 that's also going to give me 255. So this is what's interesting here about hexadecimal. It turns out that an upside of storing values in hexadecimal is that we're going to see the first F sort of represents the left half of all these bits. And the second F, in this case, represents the rightmost 4 of these bits. So it turns out hexadecimal is very useful when you want to treat data in units of 4. It's not quite 8, but units of 4. And that's not bad, which is why if you use 2 digits, like I have thus far, 0, 0, or FF, or anything in between, that's actually a convenient way of representing 8 bits in total. 1 hex digit for the first 4 bits, 1 hex digit for the second. And again, there's nothing new intellectually here per se. It's just a different way of representing the same story as before, zeros and ones. So in what context do we see this? Well, we talked about memory last week, and we're going to talk more about it this week. If this is my computer's RAM, random access memory, you can again think of each byte as having a number associated with it, like its address or location. This might be 0. This might be like 2 billion. And so in the past, I described these as just this, using decimal numbers. Here's byte 0, 1, 2, 3, 4, 5, 6, 7, 15, 16 would be here, and so forth. But it turns out in the world of memory, and thus today programming, people tend to count memory bytes using hexadecimal. Partly just by convention, but also partly because it's a little more succinct. And again, each digit represents 4 bits, typically. So what comes after F here? Well, if I think about the computer's memory, I normally might do after F, which is 15, 16, but instead 1, 0, 1, 1, 1, 2, 1, 3. This is not 10, 11, 12, 13, because I claim them in the context of hexadecimal now. As per the previous slide, we already started going into A's through F's. So you immediately see here a possible problem. Like, why is this now worrisome if all of a sudden you're seeing seemingly familiar numbers like 10, 11, 12, 13? We didn't really stumble across this problem when it was like all zeros and ones before. Yeah? Yeah, so if you're writing some code in C that's doing some math, you might accidentally, or the computer might accidentally confuse hexadecimal with decimal if they look in some context the same. I mean, any number on the board that doesn't have a letter is ambiguously hexadecimal or decimal at this point. And so how might we resolve this? Well, it turns out that what computers typically do is this. By convention, anytime you see visually 0x and then a number, that's a human convention of signaling to the reader that this is, in fact, a hexadecimal number. So if it's 0x10, that is not the number 10. That is the hexadecimal number 10, which, recall we said earlier, is how you count up to 16. And again, these are not the kinds of things to memorize. It's really just the system for how you think about these things. So henceforth today, we're going to start seeing hexadecimal in a bunch of contexts. When you write code, you might even write code using some hexadecimal. But again, it's just a different way of representing numbers, and humans have different conventions for different contexts. All right, so with that said, any questions now on this building block? But here on out, we'll start using it in some actual code. Any questions? Nothing so far? All right, so let's go ahead and consider maybe a familiar example, something involving code where I initialize a variable like n to a value like 50 in this case, and then let's start to tinker around with what's going on inside of the computer's memory. In a moment, I'm going to load up VS Code on my computer, and I'm going to go ahead and whip up a program that very simply assigns a value like the number 50 to a variable called n. But today, keep in mind that variable n and that value 50 is going to be stored somewhere in my computer's memory. And it turns out today we'll introduce a bit more syntax so you can actually see where things are being stored. So let me click over to VS Code here. I'm going to create a program called address.c just to explore computers' addresses today. And I'm going to do an include standard io.h, int main void, as usual, no command line arguments for now. I'm going to declare that variable n equals 50. And then I'm just going to go ahead and print it out. So nothing very interesting, but I'll use %i, \n, and then comma n to print out that value. Nothing here should be very interesting to compile or run, but I'll do it just to make sure I didn't make any mistakes. Looks like, as expected, it simply prints out the number 50 like this. But let's consider then what this code is doing underneath the hood when it's actually run on your machine. So here we have that grid of memory. That variable n is an int. And if you think back, how many bytes typically do we use for an int? Yeah, 4. So 4 bytes or 32 bits. So if each of these squares represents 1 byte, then my computer somewhere in my memory or RAM is using 4 of these squares. Maybe it ends up over here just because there's other stuff being used elsewhere, for instance. Though I don't really know. And frankly, I don't really care where it ends up, just that it ends up somewhere. So the value 50 is stored here in a variable called n. Even though I've written it as decimal, just like in my code, let me again remind that this is 32 zeros and ones representing that 50. It's just going to be very tedious if we start writing everything in binary, so I'll use the more comfortable human decimal system. So that's what's going on inside of the computer's memory. So what if I actually wanted to start tinkering with its location, or maybe just knowing its location? Well, this variable n indeed has a name, n. That's a label of sorts for it. But at the end of the day, that 50 is technically at a specific address. And I'm going to make one up, 0x123. And it's 123 because I really don't care what it is. I just want an address for the sake of discussion. So way over here off screen might be byte 0. Way down here is byte 0x123. It's in hexadecimal notation just by convention. So how can I actually see where my variables are ending up in memory if I'm curious to do so? Well, let me go back to my code here. And let me actually change this just a little bit. Let me go ahead and introduce, for instance, another symbol here and another topic altogether, namely pointers. So a pointer is a variable that stores the address of some value, the location of some value, or more specifically, the specific byte in which that value is stored. So again, if you think of your memory as being a whole bunch of bytes, 0 at top left, 2 billion or whatever at bottom right, depending on how much RAM you have, each of those things has a location and an address. A pointer is just a variable storing one such address. So it turns out that in the world of C, there's a couple of new symbols we can use if we want to see what it is we're talking about here. And those two operators, as of today, are these. You can use the ampersand operator in C in a couple of ways. We already saw it very briefly to do ampersand, ampersand, to kind of and two Boolean expressions together in the context of a conditional. This is different. A single ampersand is the address of operator. So literally in your code, if you've got a variable like n or anything else, and you write ampersand n, C is going to figure out for you what is the address of that variable n in the computer's memory. And it's going to give you a number, otherwise known as the address of that. If you want to store that address in a variable, even though, yes, it's a number, like 0x123, you have to tell C in advance that you want to store not an int per se, but the address of an int. And the syntax for doing that, somewhat non-obviously, is to use an asterisk here, a star operator. And you say this when creating the variable. If you want p to be a pointer, that is the address of some other variable, you do int star p. And the star just tells the computer, this is not an integer per se. This is the address of something. That yes is an int, but we're just being more precise. So on the right-hand side, you have the address of operator. As always, with the equal sign, you copy from right to left. Because ampersand n is by definition the address of something, you have to store it in a pointer. And the way to declare a pointer is to specify the type of value whose address you're storing, and then use the star to indicate that this is indeed a pointer and not just a regular old int. So let's see this in practice. Let me go back to my own source code here. And let me make just a couple of tweaks. I'm going to leave n alone here. But I'm going to go ahead and initially just do this. Let me say int star p equals ampersand n. And then down here, I'm going to print out not n this time, but p, the variable p. And then even though, yes, it's just a number, and therefore I kind of sort of could use %i for integers, there's actually a special format code in printf for printing pointers or addresses. And that's %p. So now let's go ahead and recompile this, make address. So far, so good. /address, enter. And a little weirdly, but perhaps understandably now, the address in my computer's memory at which the variable n happened to be stored was not quite as simple as 0x123. This computer has a lot more memory, so technically it was stored at 0x7ffcb4578e5c. Now that has no special significance to me. It could have ended up somewhere else altogether, but this is just where in my computer, or technically the cloud server to which I'm connected using VS Code here, that just happens to be where n ended up. And strictly speaking, I don't even need to introduce this variable. I could get rid of p, and I could just say print not just n, but the address of n, and achieve the same thing. You don't need to temporarily store it in a variable. Let me just do make address again, /address, and now I see this address here. And notice if I keep running the program, it's actually moving around. There's other stuff presumably going on inside of the computer. Maybe it's actually randomizing it so it's not always at the same location. That can actually be a security feature underneath the hood. But this happens to be at that moment in time where that value is in memory, quite like our picture a moment ago. All right, so let me pause here to see if there's now any questions on what we just did. Yeah?
Is there any way to control where you are storing something in memory? And does it even matter or does it just matter that you can go in and locate where something is?
Really good question. Is there any way to control where something is in memory? Short answer is yes. And this is both the power and the danger of C. And we're going to do this today and make a few deliberate mistakes, because with this power of going to or getting the address of any variable, I could just arbitrarily right now write code that stores a value at like byte 2 billion or 0 or anything in between. But that also means potentially I could start kind of creepily looking around at all of the computer's memory, even at things that I didn't put there, maybe other programs, maybe other parts of programs. And indeed, this is a potential security threat. If suddenly you're able to just look anywhere you want in the computer's memory. Now, I'm overselling it a little bit because nowadays in this decade, there are some defenses in place in compilers and in our operating systems that do hedge against this a little bit. But this is still a very frequent source of problems. And later today, we'll talk briefly about things called Stack Overflow, which is not just a website. It is a problem that you can encounter. Heap overflow and more generally buffer overflows. There's just so many things that can go wrong using this language called C. And if any of you have encountered a segmentation fault yet, I think we saw a few hands for that already, you touched memory that you shouldn't have. And odds are you did it most recently by going too far in an array, going to the left or negative in an array, or somehow looking at memory you shouldn't have. And we'll explain today why it is you were able to do that. Other questions on these primitives so far? Yeah, from Carter? Good question. Earlier we used star p. Let me rewind in time to the previous version of this code where I actually had a variable called p. Just like with variable declarations in the past, once you've declared a variable to be an int, a char, a bool, or an int star, aka a pointer, you don't thereafter keep using the word int or now the star. Once you've declared it, that's it. You only refer to it by name. And so it's very deliberate what I did here, saying that the type here is int star, that is a pointer to an int. But here, I just said the name of the variable, as always. I didn't repeat int, and I also didn't repeat star. But at the risk of kind of bending one's minds a little bit, there is unfortunately one other use for the star operator, and that's as follows. If you want to print out not the address of something, but what is at a specific address, you can actually do this. If I want to print out the integer via %i that is at that address, I can actually use the star here, which technically contradicts what I just said, but it has a different function here, different purpose. So let me go ahead and do this in two different ways. I'm going to leave this line of code as is, but I'm going to add another line of code now that prints out what apparently will be an integer in a moment. So %i\n. And I could cheat, and let me just do n for now. So there's really nothing special happening now. I'm just adding a sort of mindless printing of n. So make address, /address, there's the current address of n, and there's the value of n. But what's kind of cool about C here, too, is if you know that a value is at a specific address like p, there's one other use for this star operator, the asterisk. You can use it as the so-called dereference operator, which means go to that address. And so here what we actually have is an example of a pointer p, which is an address like OX123 or OX7FF and so forth. But if you say star p now, you're not redeclaring the variable, because I didn't mention int. You're going to that address in p. So let me recompile this now. Make address, /address. And just to be clear, what should I see? I'm first going to see the pointer itself, OX something. What's the second line of output I should presumably see now? Just shout a little louder. So I'm hearing 50. And that's true because if you figure out the address of n and print it in line 7, but then go to the address of n, aka p, that's indeed going to just show you the number n, the value of n again. All right, any questions now on this syntax? And I will concede, I think this is confusing. The fact that we use the star for multiplication, the fact that we use the star to declare a pointer, but then we use a star in a third way to dereference the pointer and go to the pointer. It's just confusing, honestly. But with practice comes comfort. Yeah?